Hi everyone, today we're going to be looking at how to determine the displacement of an object from a from a velocity time graph and then derive an equation from that. So the one thing that we did talk about before, I just want to remind you, is the fact that when we find the area underneath a velocity time graph, so this is the area here and here, we're going to be finding the displacement of the object. So what we're going to do is to find the area, we're going to find the area under this line and the x-axis, which is over here. In order to do that, we're going to have to divide this section here into area 1 and then area 2, the two areas over here. The things we have to keep in mind when we're doing this section over here is going to be the change in time. This area is going to be, or this section here is going to be V1. And this distance here is not going to be V2, but actually it's going to be the difference between V2 and V1. So just remember that when we're doing this. So let's do a little bit of calculations here. So again, to find the area or the displacement, we're going to find the area here, for area 1 and area 2, and add them together. So for area 1 over here, we're simply going to find the area of the shape here, so it'll be V1 multiplied by the change in time. And then for the second area over here, it's a triangle, so we're going to use 1/2 the base, which happens to be delta t, times my height. And my height in this case is V2 minus V1. Okay? This is going to be the first part of our actual equation. Now, something I do want to do, and I want to remind you of, is the fact that we do have this equation here as well. So we know that the acceleration is equal to the change in velocity over the change in time. You can see that we've got V2 minus V1 in both of these equations. We're going to actually combine them. So let's bring the time over. So we're going to end up with acceleration times my change in time is equal to V2 minus V1. So what we're going to do is we're going to take this and bring it into this part of the equation there. Okay? So let's see what happens when we do that. So I'm going to have my displacement is equal to my V1 times my time plus 1/2 my time. Now instead of writing down V2 minus V1, I know that V2 minus V1 is equal to AT. So acceleration times time. Let's use this color here. Let's use a different color. A little bit clearer for us. Let's use red. So my acceleration times my time, change in time. And when we do this, here's what happens. We're going to have our displacement is equal to V1t plus 1/2. I'm going to bring the A over here. And then the time is going to be 2t, so time squared. And this is our new equation. So our equation is going to be the following. So it's going to be my displacement is equal to V1t plus 1/2 AT squared. Sometimes I'll write it like this just to simplify it. Oops, sorry, V1t plus 1/2 AT squared. And one way I like to remember this equation, makes it a little bit easier, is to remember the following saying. D vit hat squared. So D vit hat is the half and the A, the T, so hat squared. So D vit hat squared, and you remember this particular equation. So this is now our third equation. So remember, we had our constant velocity equation, we had our acceleration equation, and now we have our third equation we can use with acceleration based on the area under a graph. Let's look at a few examples with this equation. So in this example, we've got a kangaroo, and it leaves the ground with an upwards velocity of 7 meters per second and downward acceleration of 9.81 meters per second squared. And we want to know what is the displacement or the height of the kangaroo after 0.71 seconds. So here we've got a time. I've got an initial velocity over here. I'm going to have an acceleration. and I want to figure out my displacement. So when we look at the equations, the most appropriate equation in this case would be the one we just did. So the first thing we're going to do is we're going to define our positive direction. I'll use up as positive. It really doesn't matter, though, in the end, what we choose. So up is going to be positive. Write down what we have in terms of our given. So I know that my initial velocity was 7 meters per second upwards. I know that my acceleration is 9.81 meters per second squared down. So I'm going to put a negative in front there. And I know I'm going to have my time. So I know what happens after 0.71 seconds. And I'm going to be trying to calculate the displacement of the kangaroo in this case. So as I said, when we put all of these together, the most appropriate equation to use would be this one. So the one we just did. So the vit, d vit hat squared equation. It has the displacement we're trying to find, the initial velocity over here, the time, and the acceleration. So let's plug some numbers in here. So when we look at this, and put the arrow there. So my initial velocity, remember, was 7.0 meters per second, positive because it's upwards. My time, 0.71 seconds. Over here, I'm going to have 1/2 times my acceleration. Now my acceleration, remember, is negative. It's downward. So negative 9.81 meters per second squared. And my time is 0.71 seconds. And don't forget to square that. A lot of people forget to do that. So really be mindful of that. So when we calculate this, 7 times 0.71, we end up with 4.97. And the units cancel here. We end up with meters. Over here, we're going to end up with 0.5 times negative 9.81, so 4.95 negative, times 0.71 times 0.71, which gives us a negative 2.47. And notice the second squared cancel. We end up with meters. And we put all this stuff together. We end up with 2.49 meters. So basically, the kangaroo traveled 2.49 meters upwards because it's a positive value. So let's write down a little therefore students. So therefore, the displacement of the kangaroo and with significant digits is, so let's look up here, we got 2, 3, and 2. So least number is going to be 2. So we round this to 2 significant digits. 2.5 meters. It's a positive number. Positive was upwards. 2.5 meters upwards. In other words, we know that the kangaroo during this motion traveled 2.5 meters upwards. Okay, so that's it for that example. Let's look at one more. So in this case, we got Lori trying out her new downhill skis on the Bunny Hill at a ski resort. She started moving from rest. It's going to be important, so it's going to be our initial velocity at the top of a hill and skied 105 meters downhill. So that's going to be my displacement. And this happened in 18 seconds. I want to know her acceleration while skiing down this hill. So in this case, what I probably want to do is I want to make down positive. So most of the motion will be downwards in this situation. So down is positive. So she started moving from rest. I know my initial velocity is 0 meters per second. She did have a displacement of 105 meters downwards. Remember, down is positive. And she did this in 18 seconds. And what I want to do is I want to find her acceleration during this motion. So in this case, what we have, we're using the same equation. So my displacement, d vit hat, we forgot the delta, but it's there, squared. So we know our displacement. Let's plug our numbers in. 105 meters. My initial velocity is 0, so it's just going to be 0, plus 1/2 a, my acceleration. And my time, remember, was 18 seconds squared. So we're going to clean this up a little bit. So I'm going to multiply both sides by 2 to get rid of the half. So it'll be 2 times 105, so it'll be 210 meters equals 80 times 18 seconds squared. Now I have to get rid of this 18 seconds squared, so divide both sides by that. Over 18 seconds, don't forget squared. That's going to be my acceleration. And when I do all of this, I'm going to get a number of 0.648 meters per second squared as my acceleration.
How do you do that?
Shh, leave me. So therefore, acceleration.
Can I try?
Hold on, Michaela. You can say hi to everybody in a minute. Is 0 point and significant digits. We've got 2, I think. 65 meters per second squared. And remember, positive is positive, so down was positive, downwards. Okay, and that's it. So that's it for this component of the video. Michaela, you want to say bye to everybody?
What?
Say bye to everybody.
Bye.
Okay, good night.